Networks are interesting because they tell us something about the social world, where people fit into their into social life. But they're also interesting because when we're connected to other people, we actually share some of their experience too. So we, if I'm tied to David, for example, he might give me an idea that I might use. We might develop a shared norm or something like that. And so in general, we think that things flow over social ties. And that's one of the major reasons that we care about networks. And so in general, so what the process that I'm going to be talking to you about today is diffusion, which is essentially this process for things spreading through the social ties between people. So I've drawn out a toy network to show you kind of what I mean at a very simple level. To be honest, this is going to sound a little bit simplistic, and it's really actually a very, very simple and straightforward idea. So I don't want you to get too bogged down in like the, oh God, there's math. Because really, fundamentally, all we're talking about is these two people are connected, and something can spread from person A to person B. So for example, if we have like a disease that, let's say we're talking about HIV, for example, and these blue people are susceptible, and these orange people are infected with HIV. And let's say that the network ties are indicating shared needles, for example. So these two people share needles, these two people share needles, and these two people share needles. And so what we might expect is that over time, if these two people continue sharing needles, eventually this person might contract HIV, and then this person might contract it, potentially from this tie or from this tie, or some additional process of sharing needles. And then this might ultimately spread through all of the people in the network. And so that's really the main idea that's underlying all of this. And it is fundamentally an epidemiological idea, but as Jim mentioned, it's been expanded to include a wide variety of different possible things that could spread between people. So we could start with thinking about HIV, or thinking about the flu, and thinking about things, an actual disease that spreads between a group of people. But we've also come to think of this in terms of behaviors or innovations or other things, other concrete activities that people might begin to take up as a result of their friends. So this Krieger and Haney paper was looking at binge drinking. So when if your romantic partner's friends take up drinking, then you're more likely to take it up, presumably because your partners do what their friends start to do, and then you do what your partner starts to do. How many people think being fat can spread through a social network? How many people don't think being fat can spread through a social network? Okay, good. Don't be shy. It's okay if you don't think that that can actually happen, because there was actually quite a bit of controversy over this article. This was about 10 years ago. Christakis and Fowler put together an article using the Framingham Heart Study, where they actually tried to show that obesity could spread through social networks. So people who are connected to each other were more likely to be obese. There's been a long string of debates about whether or not that could happen, and partly because it's not entirely obvious what the mechanism was. So was it that you and your friends develop share exercise norms or share norms about what foods you're going to eat? Or is it just some kind of genetic not genetic clustering? I mean, potentially it could be families where obesity runs in the family, or potentially it could be any number of things, any number of reasons why they were connected to each other. And so that is, as we get further and further away from the idea of diseases spreading through the network, it becomes murkier and murkier about how it's actually happening. Although that said, increasingly newer papers have started to look at the actual specific mechanism. So a relatively recent paper took advantage of differing weather patterns as a source of exogenous variation to look and see whether or not exercise spread through a social network, and in fact found that it did. So there is some possibility that behaviors like innovation, or behaviors like drinking, like exercise, like eating behaviors might spread through a social network, and those might have concrete impacts on health outcomes. Another area that I don't have on this slide that's actually quite important, or potentially quite important as well, is the diffusion of innovations. among organizations. So this, I'm thinking of this in terms entirely of individuals, of things like ideas and behaviors and practices spreading between individuals, but you can actually think of this as a super individual level. So if a health department develops one thing, how does that best practice spread to the next health department and the next health department about that? If everyone, for example, has an NHBS grant, do only cities that have an NHBS grant adopt certain practices? And do they do that because they all met at the conference in Atlanta every year and talk about what, oh yeah, we're doing this? Or is it something else entirely? Does CDC come down from on high and say, this is how you have to do things? So you can imagine there are a lot of different ways that this could impact health outcomes. Again, the last possibility is that we could think of even ideas or attitudes or beliefs spreading through a social network of people. So it's not just diseases or things that you could contract by contacting people, but also you could think of an idea or a rumor as being infectious, and you could imagine that people would start to converge on those beliefs, and those beliefs might affect their health behaviors as well. And so while this does start with an epidemiological framework of things spreading through a social network, there's actually quite a few applications of this. In keeping with the fact that this starts, first of all, this is a health conference. And second of all, because this is a health metaphor, I'm going to start by talking briefly about compartmental models, so susceptible, infectious, and recovered. And when I say briefly, I mean very briefly. And then I'm going to talk about essentially how we can generalize that into a network model. And then from there, what the different transmission processes we think of for a network model are. So I'll talk about three in particular. First, I'll talk about how diseases diffuse, which is one process of just basically repeated contact over a certain set of ties. Then I'll talk about how we think behaviors diffuse, which I'll treat more or less as the same as the diffusion of an innovation. So after a certain threshold of your friends have adopted something, you'll want to take it up as well. And then finally, I'll talk about how ideas and attitudes diffuse, which we generally think of as a weighted averaging process. So if half of my friends believe smoking is cool and half of my friends believe smoking is not cool, maybe potentially I might change my mind and meet up in the middle. As I'm describing that, hopefully you're thinking to yourself, well, I don't know if that's actually true. Is that really how that works? Like that if half of my friends believe one thing and half of my friends believe the other thing, I just meet in the middle? And it's probably not. And that's where a lot of the current research is moving, is to say, how do we think about diffusion in circumstances where, or like essentially, how do we think about this process? Because this process is very well understood for a disease like HIV, and it's very poorly understood for an idea like whether or not you think smoking is cool. And so I'll talk a little bit about some of the current challenges in the literature and the directions that we're trying to take trying to push it forward. And hopefully that will spark some great ideas, because I think this is a field that could use some really interesting ideas and some new data. All right. So starting off with the epidemiological model. So let's start by talking about the first idea, which is that diseases can spread between a set of people. So the standard model is what we'll call a compartmental model, and you'll see in a minute why I'm calling it compartments, but the general thought is that people are kind of in a population randomly bumping into each other, and then as the result of one of those contacts, a disease might spread from person A to person B. So imagine that one of you has the flu. I really hope one of you does not have the flu. But imagine one of you does, and we're all in this room, and we're all randomly wandering around and periodically talking to each other and going over to the food. And so if the one person who has the flu bumps into people, they have some probability of spreading the flu to the next person in the network. And so sometimes, if you imagine, again, these orange people are infected and the blue people are susceptible, you might imagine that there are a few people with the flu, and if they bump into each other, they're not going to give each other the flu because they both already have it. And then there are a bunch of people who don't have anything, or who don't have the flu, and if they bump into each other, nothing's going to happen because they don't actually, neither of them have the flu. But then occasionally you'll bump into someone who does not have the flu will bump into someone who does have the flu, and then with some probability, that person, with that discordant tie, so in other words, that tie where there's a susceptible and an infected who bump into each other, we might expect to see that susceptible person get infected with some probability. this is actually relatively well represented by a system of differential equations, which I'm really not going to talk about that much, because it's important, but maybe not super important for what we're going to talk about today. But the notion here is that there's a bin, there's compartments, essentially. People fall into different compartments. So there's a bin of people who are susceptible, there's a bin of people who are infected, and there's a bin of people who have recovered from the illness. Or I guess the other way of putting that is removed. So they either recovered or died. And then there's some probability of moving between each of those bins. So there's the probability of infection, there's the probability of recovery, so beta and gamma. And then the way that the change in each of those bins is roughly proportional to the probability of being infected in a given instance, and the relative size of both of those bins. So if there's if there's a lot of susceptibles and a lot of infecteds, then the number of infecteds, or the number of susceptibles is going to decrease, the number of infecteds is going to increase, and things like that. Does that make sense? So it's just the contact probability times the number of people in the different bins. But that's assuming that everybody is kind of bumping around, that we're in just this giant room, right? And everybody's kind of bumping around, running into each other, and any given contact has a certain probability of people actually getting sick. I should point out, actually, before I go, sorry, forgot that this was in there. So anytime you have a disease spreading, that will lead to what we'll call a logistic growth curve, or an S-shaped curve. It's a characteristic shape of one of these things. It's kind of a necessary, it's a necessary outcome of growth in a constrained population. So if this is the number of people who have the flu, and once you get the flu, actually let's say it's the chickenpox. Once you get the chickenpox, you can't get rid of the chickenpox, right? So at first, there's a small number of people who have this disease. As that number of people grows, it starts to take off exponentially, because they have, if one person infects two people, and then those two people infect two more people, you get this kind of exponential growth, right? And so it starts to take off. But then at some point, there's only so many people in your population. And so at some point, this exponential growth can only go so far, and there's only so many more people that we can infect at a given time, and eventually it levels off at everybody being infected. You'll see this come up again and again in the diffusion of innovations. This is called an S-shaped curve, but it's really just a logistic growth curve for the number of people who are infected at a given time. Now that's true of both a compartmental model and a network model. I'll distinguish between, so when I said the compartmental model, I think of people being in a room, randomly mixing, like they bump into each other somewhat at random. But that's not necessarily a good model for how, for example, sexually transmitted diseases spread between people. So with sexually transmitted diseases, it's only being spread over sexual contact or shared infectious drug use. And that's really where the network model started to be developed for the disease diffusion models. So instead of thinking of all of these people kind of randomly mixing in a room, we start to think about more particularly what the specific ties are between the people and whether or not things can spread over a particular tie. So instead of so for example, we could still say that these two people, there could be an infection that happens between these two people if they, after a given contact. And we could still say that these two people, there's unlikely to be an infection after a given contact. But we would not say that there's some possibility of direct transmission from this person to this person, right? Because there's just no way, because these two people in our sexual contact network, these two people aren't having sex, the infection would have to spread through this person, and then this person, and then this person. And that can actually lead to a fairly different set of outcomes. And in particular, one of the main areas that we've been looking at in that one of the main areas that we've been looking at for that is for the time ordering of the ties. So for example, if this is a random mixing, it doesn't really matter if this tie happened first or this tie didn't happen. Everybody's bumping around in a population, and all they have to do is occasionally run into each other. But if this tie was present and this tie was not, or if this tie was not present and this tie was, and then this tie became present and that tie didn't, then you might expect the infection to get this far and no farther. And so I've drawn that out a little bit, and I'll actually spell that out in a little bit more detail as we go forward. But the notion here is that if this tie is present at time 1 and that tie is present at time 2, then you could see the infection progress the way you would expect. You know, it spreads from person to person to person. But if you reverse the ordering, where this tie is present at time 2 and that tie is present at time 1, then the infection stops. And that's as far as we can go. And so that's actually where we start to see the network models become somewhat more interesting, particularly for disease diffusion. Because in fact, when we talk about a network of people who are tied to one another for a sexual contact network, so for example, you've seen Jim showed the visual of the Colorado Springs sexual contact network. That doesn't really contain any timing of the ties. So it makes it look like everybody's connected and things could spread all the way through the town. But that's actually not necessarily true. So what that's doing is that's conflating 3 relevant networks. The first network is the contact network. So that's generally, have these people ever, just basically binary connections, have these people ever had sex at any point, or have they ever shared needles at any point in time? And so in this case, under the contact network, A can reach everyone. But let's say for a moment that these numbers indicate the timing of the ties. So this tie was present at time 1, this tie was present at time 2, this tie was present at time 3. Who can A actually reach? I'm actually going to ask. So get a little audience participation. It's the afternoon. I know you all are tired. Don't be shy. It's easier than you think. Anyone?
Can you repeat the question?
Yeah. So given that these, okay, so if all these ties were happening simultaneously, if an infection starts with person A, how far could it go? Right. So it could go through everyone. But now instead, let's think about the ties as happening when they're at the numbers that they say. So this tie is happening at time 1, this tie is happening at time 2, this tie is happening at time 3. Now how far could the infection spread if it starts at person A? Just to C. OK, why is that? Yeah, so it could spread to person C. It could spread to person D. It could spread to person B. Yeah, it could spread to person K. Right, so it could also get to L. John, it's no fair if you answer. I know. Let someone else figure it out. Right, OK. So let's walk through that. How does that happen? Right, exactly. Who's someone it can't spread to? Exactly. Why is that?
Because N only had one relationship with L, and that was at time 2, which is at the same time that A went to B, but after B went to K.
Right. So basically, at time 2, these relationships are happening. And then at time 3, it could potentially spread this far. And at time 4, it could spread this far. But at that point, this relationship is no longer happening. So it can't get that far down the network. So in fact, this network is what we'll call the exposure network. It's the second of the 2 networks. And really, when you're talking about the contact network, it looks like everyone is connected. But in fact, when you start to look at the exposure network, like the people who could potentially be exposed if A started off with the infection, it's much smaller. And so I think we established that it can get as far as O or D, but it gets cut off here because D had an early relationship that ended with person E. And it never makes it to N because N only had a relationship at time 2 with person L. So that's one aspect of the importance of time ordering. The third network that we're talking about is the actual transmission network. So we have the contact network, the people who were ever contacted, who were ever connected to each other at any point in time. We have the exposure network, which is the people who are reachable along the time ordering of ties. Like, so if you respect the time ordering of ties. And then there's the actual transmission network of if it didn't spread, if it starts off at A and it never got to B, and it didn't spread to B in time 1, or in time 2, I guess, then at time 3, this person K would never be reachable. So there is an actual path dependence here. So once, if you're actually talking about how far can this spread, with some probability, it actually does have to spread to this person, and then we have the same process over again, where the timing of the ties matters quite a bit. So far, so good? So this is one of the reasons that we think networks matters quite a bit. And it's actually come up a fair bit in the HIV world, in particular with respect to concurrent relationships. So I'm actually I'd like to try Jim and I were just talking about this as a classroom exercise, and I think the first time I did it, I screwed it up, but now I know how to do it. So let's have everybody stand up. This is a classroom participation exercise. It's a very slightly uncomfortable classroom participation exercise. So everyone, look at your neighbor, find a unique pair of people, and hold hands with your neighbor. No, just one neighbor. Everybody, one neighbor. One neighbor at a time. All right. So this is a world of serially monogamous relationships, right? Everybody is paired off in some nice, happy couple. How far could we get if I start with Ashton? Could I get to you, Nina, over there? No, right? It can only go as far as, I'm sorry, I don't know your name. Marielle. It can only get as far as Marielle. Now, everybody reach out and hold the hand of one other person who's next to you. All right. Now if I started actually, this will be fun maybe, or maybe annoying. Ashton, can you pass this and see if we can get to Nina with that via connected ties? Huh? No, just pass right and see if we can get all the way. So Nina is in the back corner. Sorry, Nina, I'm picking on you because I know your name. But let's see if we can get there along connected ties. This is via people who you're supposed to be holding hands with, right? So it's not just like randomly passing it between people. Okay, so it should have stopped there actually if they're not holding hands. How far did it get? Did it stop? Okay. But this is actually considerable. So starting with Ashton, we didn't stop at Marielle. OK, you guys can have a seat. Thank you all for being good sports and holding each other's hands. But this is actually kind of remarkable. It got halfway. So just by changing the structure of the network, it went from being stuck in the infection went from being stuck in one corner to getting halfway across the room, right? And that can really change pretty dramatically what the infection potential of a network is. And so if you draw this out, so this is the contact network, right? But if you think in terms of the reachability, the second network that we were talking about, if you have this serially monogamous network, then essentially you can get from A to B and B to C and A to C potentially, but you can't get backwards in time from C to A, right? Because these two things this happened at time 1, this happened at time 2, so it can go this way and that way. But now that this relationship is over, it can't go backwards in time. And so similarly, if you have concurrent relationships, so these two, there's an overlap in time over here. If C has the infection, then during time 2, C could pass it to B, and B could pass it back to A because there's an overlapping period of time in the network. So the concurrency matters really in two ways. One is it increases the size of the connected component. So you could get across the room much farther with the exercise that we just did. And secondly, because it allows you to go backwards in time. And so Jim and Martina Morris and a number of others did a series of simulations which actually show the extent of the transmission. So these are colored in red are the ties that are concurrent, over a particular time. But if you actually start at the seed nodes up here, if you started an infection up there, how far would you need to go, or how many ties would the infection depend on the concurrency along the way? Am I misrepresenting these? OK, good. Essentially, how far would it need to go? Like, we'll color the tie red if it relied on a concurrent tie previously in time. So that is to say, like, if it had to go, if you had to have an overlapping period like this for the tie to move here, then we're going to color this section red. So in that case, we went from having only a relatively small number of concurrent ties. You can see a few reds interspersed with the blues. So that's, in this case, we're just coloring the cases where there are concurrent ties red. But if you look at how far the disease spreads as a result of the concurrency, you can see that the vast majority of these people would not have been reachable in time except for the concurrent relationships. And so that's one of the reasons that we think of this network ties as being fairly important. So we think of them as constraining how disease diffusion can spread through a group of people. And there's been a series of simulation papers that have looked at how the network structure and topology influence ties, or excuse me, influence the disease potential. That was one. So remember, we were going to talk about 3 different types of diffusing processes. One was the epidemic process, so things spread over repeated contacts. The second, and as we move away from epidemics, we start thinking about, well, what if it's a behavior that's spreading, or what if it's an idea that's spreading? So there was a series of actually a fairly long stream of literature that thinks about what happens. Well, what if an idea spread like a disease? What if a rumor spread like a disease? These are like urban legends. Everybody has had this thought, I think, at some point. Like, I feel like this disease or this rumor is spreading like wildfire. And so, like, how do we actually model that in a concrete way? And the way that we've looked at that is like slightly different than how we've thought about epidemics. So as opposed to a repeated contact where I have to periodically bump into you and there's some probability of transmission, instead we think of it in terms of like how many of your friends are actually doing this. Like, we just kind of assume that there's ongoing contact between you and your friends, and you pick up the activities of your friends if you're connected to enough of them. So these threshold models actually, I think probably one of the first places to look at these was a paper by Mark Granovetter talking about threshold models. And he was thinking of this in terms of riots. So if you've got a bunch of people who are standing around in a crowd, how does that turn into a riot very, very rapidly? And his thought was that if enough of your neighbors nearby in that crowd start rioting, then you might feel like that's the appropriate thing to do. And so a small local cluster of people might actually spur a cascade where everybody starts to riot. Now that said, you could think of that threshold as being quite high. So a person standing peaceably in a crowd is pretty unlikely to riot. So in this case, let's consider our network again. And this time, let's think of it as directed. And so in this case, we often think of directed ties as I named so-and-so as a friend on a survey. So like, I think of this as the back page of that Prosper survey where you've got 7 lines. And some kid is writing down, Johnny is my friend, Billy is my friend, Janine is my friend, and so on like that. But you could think of it that way, or you could think of it as these are people I pay attention to, or something like that. And so, for example, this person pays attention to this person, but this person does not reciprocally pay attention to that person. And then you might say, OK, well, if over 90%, this is some behavior that I'm really, really resistant to. So it's going to have to take like 90% of my friends to do that for me to actually participate in it. Would that behavior, so like saying again that these people are susceptible and the orange people are infected, would anybody actually change their behavior in this network? If with a 90% threshold? No, you're shaking your head. Why not? In the white, I'm sorry. So like this person, for example, 60. What fraction of their friends are actually
60.
Right. Actually, Yeah, we'll do this person because it's a good example. So actually, let's start with this person. What percent of this person's friends? 0, right? Yeah. Okay. And what fraction of this person's friends? Oh, well, that's actually a bad example because that's 0. But this person, so the people that they name 1, 2, 3, 4. They never named this person as a friend. So this is where we start to pay attention to direction of the ties. And so of those, 1, 2, 3 are infected or have adopted whatever this behavior is, and one of them has not. And so that gives us 3/4 of their friends are doing this. Actually, when I first wrote out these slides, I wrote them out as undirected and realized it was in fact 2/5, or 3/5 rather. So you were right about that. Yeah.
The orange node at the top, could that person change his mind and decide not to riot because both his friends are blue?
I'm sorry, I can't quite hear you. Can that person change their mind?
The orange node at the top, can he change his mind and decide not to riot because 100% of his friends are blue?
Yes, that's a great question. And yes, I will come to that. But yes, the thought is that potentially this influence could go both ways. So for the time being, I'm going to be talking about this behavior. In this case, I was referring to this as rioting, but you could think of it as smoking or something like that, spreading from people who have already adopted it to people who have not. But you could think of the reciprocal relationship as well. I will say that that is one of the open challenges, and it's something that's fairly poorly understood, which is when do people actually abandon something that they've adopted. So right, okay, so nothing happens if we set the threshold at 90% of your friends. But if we set it at 3/4 of your friends, then we might see something, right? So we already established that this person has 3/4 of their friends who have adopted this behavior, and so they're going to change. And now what happens? I feel like I should put on Jeopardy music. Well, let's look at a person here, for example. What fraction of this person's friends have adopted this behavior? 100%, right? So now this is over that threshold, and they're going to adopt it. What about this person? So 50%? 2/3. OK, so this person shouldn't adopt. Right. OK. And so that's what we get. And let me make sure I didn't do the slides wrong and make that person adopt. OK, but what happens now, right? Nothing changes. So this person still has 2/3, and this is essentially bifurcated. So you've got a set of people who have adopted and a set of people who are like, this never crossed my threshold. That's it. And so again, the network topology, the combination of the network topology and the threshold can actually influence how far this cascade spreads. We'll try it one more time with 50%. So again, this person will adopt, this person will, oops. But now, since this person was at 2/3, that's above their threshold, and they'll start adopting. And then you can see it cascade through the rest of the people in the network. And so this is generally what we think about for threshold models. Now, I actually did want to spend a little bit of time writing this out as a matrix multiplication problem. This may seem like something like, oh, R does this. Why would I do that? But I think it's actually quite enlightening to understand the interplay between like how this actually works out. So let's say we have person 1, 2, 3, 4. How did I do this? 5, 6, 7, 8. OK, those are the people in the network. So person 1 is connected to person 2. Person 2 is connected to person 3. Person 3 is connected to person 2, 3, and 4, and so on, right? So this is just the adjacency matrix that Jim was talking about. And then we can represent we're going to call y the binary variable indicating whether or not people had actually adopted this at a given time. So at person 4, 5, and 6, or sorry, 4, 7, and 8 have adopted. So 4, 7, and 8 have adopted this so far. How many people actually remember how to do matrix multiplication? OK. Good, that's what I thought. So we're just going to do this real quick, because I think that'll make that actually slightly easier going forward, especially when we start to futz with R. So for person, let's take, so essentially the deal is so say you have a matrix that looks like this. The way that you do the matrix multiplication is you multiply each row by the column. So you do A times E plus B times F for the first row, first column. And then second row, first column is CE plus DF. OK? So far, so good? So then to actually do the first one that we were, so to figure out the threshold for this person, or to actually do this matrix multiplication for this first person, what we have is essentially we have the first row, which is 0, 1, 0, 0, 0, 0. How many? 1, 2, 3, 4, 5, 6, 7, 8 times 0, 0, 0, 1, 0, 0, 1, 1. Did I get that right? It's easy to guess wrong because this is going to wind up being 0, as you might see in a second. But essentially, we're going to have 0 times 0, 1 times 0, 0 times 0, 0 times 1. So it'll be 0 times 0 plus 1 times 0 plus, and so on. Does that make sense to everybody? OK. Let's, can I erase this? Yeah, OK, good. All right, let's do one that's actually going to turn out to something so you can see what we get. So we know that this one is supposed to wind up being 3/4 of their friends, right? And so that person is person 5, I think, which is, I think I may have this reciprocal when it's not supposed to be. But that'll be this row. So it's 0, 0, and I have 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. Times 0, 0, 0, 1, 0, 0, 1, 1. Thank you. OK. This is actually, I'm going to make a note here. This should be a 0. Just FYI on the slides. OK. Anyone remember? Anyone want to try this out? OK. This is actually probably going to be pretty hard to get someone to raise their hands and do it. So we'll just draw out what this is essentially. So it'll be 0 times 0 plus 0 times 0 plus, this was supposed to be a 0, so that's a 0 times 0 plus 1 times 1 plus 0 times 0. And then we've got 0, 1, 0. So it'll be 1 times 0 plus 1 times 1 plus 1 times 1. This is a very long and complicated way of writing 1 plus 1 plus 1, right? Which equals 1 plus 1 plus 1, which is 3. Did that give me what I wanted? No, actually, it did not. Because now I've got the number of friends that they're connected to who have infected, but not the percentage, which was what we were looking for. So what we actually need to do to get the percentage, is we actually need to row normalize this matrix of weights. And when I say row normalize, what I mean is divide by the sums of the rows. So in this case, there are 3 people in the row. We say we're going to divide each of them by 3, and so it'll be 1/3, 1/3, 1/3. This person will be 1/2, 1/2, and 1/4, 1/4, 1/4. And then, so then if I were to do this again, instead of multiplying by 1, I'd be multiplying these by 1/4, and I'd get 3/4, right? Which will actually look something like this. Now this gets to your question about whether or not people could abandon. So under this model, the way that we have this set up, now the people who are connected to people who don't adopt the behavior actually wind up having zeros as their peer influence score. we start to think that that they actually would be abandoning as a result of the non-adopters, right? And so if you really want to if you're trying to do this in a kind of a kludgy way, you could you could set the diagonal equal to 1. And so in this case, the diagonal is a way of thinking of how much people weight their own behavior or their own previous beliefs. And so in that case, because this threshold is between 0 and 1, it's always gonna force those people to stay adopted, and you're going to wind up with the standard logistic growth model. And so actually, this is, like I said, this is a relatively long literature on the diffusion of innovations, essentially how do things spread between people. And it's developed, I think, sort of independently of the epidemic literature, but they're quite similar in effect, right? Because it's things spreading between a connected group of people, and they actually came up with a whole typology of when people adopt. So there are like the innovators, who are the people who adopt in the first 2.5%, and then the early adopters, the early majority. There's this entire world of thinking about who adopts. And so the reason ordinarily this is the stuff of a very boring business school talk. The reason that I am telling you this here is because we often have tried to port it onto models of smoking, for example. So like maybe there are the kids who are like the innovators and the early adopters, and how do we think of different characteristics of when people adopt. And how they take up behaviors that we don't particularly want. The other thing that's worth noting in the threshold models is what I was saying relatively earlier, which is that for the time being, we were thinking of everybody having the same threshold. But if you think of people as having different thresholds, you can lead to fairly large differences in the ultimate outcome. So like if there's one person who's right in the middle of the network and who's a real holdout and they're just not going to change their behavior, then the innovation could cascade to get as far as that person, and then it would stop with that person. OK. So far, so good. So we were thinking of epidemic models. We were thinking of threshold models. One of the newer areas in threshold models, and one of the more exciting areas, is this idea of complex contagions. So the thought is, with a simple contagion, it only takes one person to let you know about it for you to actually adopt it. So if just one of my friends smokes, potentially I'll take up smoking. I keep using smoking, by the way, because that's one of the key outcome variables in the data set that I've used for a while, the Prosper data set. So I think of terms of adolescence and smoking. But you might think of contagion as happening. One of my friends takes up smoking, and maybe I'll think, oh, well, maybe that is cool. Maybe I'll try it. But for more costly behaviors, we might start to think in terms of more of your friends needing to adopt. And you can actually think of that in two different ways. One is the threshold version that I was talking about before, but you could also think of that in terms of the sum of the number of friends that you need to be connected to. So if the sum has to be more than 2 friends that I'm connected to, or 3 friends that I'm connected to, for me to really convince me to do this. Another way of thinking about this is like if my friend is trying to convince me to buy running shoes, I'll be like, meh, I don't really believe you. But then another friend tells me, and potentially I'm like, OK, well, if all of you are telling me to buy the same running shoes, then potentially maybe I should think about it. The upshot of all of that is to say that it actually, we've thought about, when you think about how networks shape the spread of an innovation, you could think that these relatively small shortcuts across the network, where a person is connected to someone who's fairly socially distant from them, could be a conduit for information. So there's some notion of, I'm drawing a blank on the word. Ron Burt. Yeah, there's some notion that this person might occupy a structural whole, and they're benefiting from being able to introduce these people to a new idea. And that notion fits quite well with the idea of a simple contagion. So there's if it just takes one person to tell me about it, then spreading things across the network will only take a small shortcut, a single small shortcut. But if we start thinking about things like complex contagions, where it takes more and more people to let me know about it, then actually what you're going to wind up seeing is something only spreading in a fairly dense cluster of people who are relatively closely connected to each other. And this idea has started to take off in the health literature. So here's one study that was looking at moods in adolescence, and they just kind of assumed that a complex contagion model was what was going on, and they started to try and find the parameters of the model that would fit their data best. But in the exercise contagion study, they actually had a look at that using a regression model and didn't find an awful lot of evidence for it. This came out this year. So basically, I think the jury is still out. I think it's an interesting idea and it's an important one, that things can take different amounts of influence for you to adopt them. But the jury is still out for how often it's going to matter. So in this case, what they were thinking of was how many of your friends, like, is it the number of your friends who run or the number of discrete clusters of your friends who run? So if it's just you have more running friends controlling for everything else, there's actually a lower peer influence score for the number of friends, but a higher peer influence score for the number of discrete clusters of friends. So it's like, if my friends from college and my friends from grad school and my friends from high school are all running that day, maybe I'll really feel like I should run versus just 5 of my friends from grad school are running that day. Yeah.
What about like interactions of those factors, like having friends who run and the number of friends who run, and also the density of your ego network, I guess, interacting together?
That's a great and open question, honestly. I think, yeah, does somebody have a microphone? Can you just say it and I'll just repeat it?
What about the interaction of those factors working together to increase the likelihood of adopting that behavior? So having friends who run may be less likely to adopt if I have friends who run who also know each other in my network.
I see. OK, so the question is, if I have friends who run and my friends also know each other, is there a unique effect for my friends knowing each other versus the friends who run? I think, is that? Well, or is there an interactive effect?
Yeah, the interactive.
Yeah. Or okay. Is there an interactive effect? So potentially, it's not just that 3 of my it's not just 3 of my grad school friends are running. It's that 3 of my grad school friends are running, and they all know each other, and they really want me to come. Is that going to actually have an interactive effect? And I think the moral of the story is we have a lot of, and if someone knows of a better study, please feel free to correct me, any of the DNAC students. But I don't think we have a lot of a very good understanding of how multiple influences combine. So when multiple friends who all know each other, I think we would expect there to be an interactive effect, where if multiple friends know each other and they're trying to convince you to run, you'd think there would be like some additional multiplier for them all knowing each other. But I don't think we necessarily know very well or have any well-validated studies of how those effects combine and in what ways, if that makes sense. So I think that's a great area if you can figure out how the peer influence process works in a little bit more granular way, I think that would be a great area to explore. Speaking of things that we don't know an awful lot about, I'd like to talk briefly about the third different way of looking at how things spread through a network. And this is thinking about attitudes and attitude change. So we talked about epidemics, where it's a disease where repeated contact makes it more likely to spread between people. And then we talked about behaviors or innovations, where we might expect that greater fractions of the people that you know make it more likely for you for something to spread between people. And then we might think of an extension beyond that, which is saying, like, well, maybe norms and ideas and attitudes spread between people in a network. Or maybe people hear from each other and they develop a shared sense of understanding or a shared norm. Potentially, we could think of that as a rumor or an idea as well. But as we move further and further away from the strict biological model, the idea of how this actually works starts to get murkier and murkier. So the best idea we have right now for how attitudes change, or at least the best model that we have right now for how attitudes change, is an extension of the threshold model that I was just talking about. So you can think of the threshold model as being a model for binary outcome. So like 0 or 1, do you smoke or not? Did you riot or not? If you switch that to a continuous variable, so like on a Likert scale, do you agree or disagree that smoking makes you look cool? You could think of it as essentially an ordinal variable, 1, 2, 3, and 5, or 1, 2, and 5. So this person strongly agrees, disagrees, someone slightly disagrees, and someone strongly agrees. And then our model for that is essentially that you would adopt the weighted average of your friends. So in this case, we're just going to give them even weights and say our prediction for whether or not you'll agree or disagree is just the sum of everybody else's attitudes divided by the number of people that there are. So in this case, it's like, well, maybe I slightly disagree because I'm connected to these two people. And again, these can be written out as a matrix multiplication problem, similar to the other one. If we were to multiply this out, so again, this is just the row normalized version of that, and you'd multiply it by the attitudes. And if you actually write it out as a matrix multiplication problem, you can set it up so that each person would have a particular value for self-weight and a weight that they give to others. And then there's the predicted value that we would give someone based on what their friends are doing at the previous time and based on their initial attitudes. So essentially, this is like saying how much are we going to weight the diagonal versus how much are we going to weight everything else in the model. So that is to say, there's like a social influence. We can say it's just basically a weighted average of a social influence component and a person's existing beliefs. Now, if we were to actually run that on a real network, so this is one of the, we'll actually do this in the lab so you can actually see where this comes from. But this is just a randomly distributed attitude value. What happens, let's actually look. So we randomly distribute an attitude value on a scale of 1 to 5 for everybody. And then we have everybody take the weighted average of their friends once, twice, 3 times, and 4 times, right? So 5 iterations of this model. And what you can see is that people start to converge on a similar set of beliefs over time. So you've got this cluster of reds. All of these people turn a little bit orange because they're all connected to a bunch of reds and a few greens. Yeah, and so then these people get a little bit more orange over here. And you can see that this all kind of descends into like a big blob of orangeness of people sort of half agreeing, half disagreeing. Everybody reaches this giant consensus in the network as a whole, with the exception of a few holdouts. So what's going on here is that these people aren't connected to anybody else. They say they don't have any friends, and as a result, they aren't changing their attitudes or their beliefs about whether or not smoking is bad. And this is actually part, yeah.
Going back to the disease diffusion, whatever, how about the vaccination? How is it going to be applied to vaccination in epidemic network? Another one is the assumption is for the disease network is one, the disease is never come back. But what if the disease can come back for the people who are recovered? And how is it going to be influence all the network and diffusion?
So coming back to this, right? So the question was essentially, we're assuming that first we're assuming that once people, A, how do we deal with vaccinations, and B, how do we deal with people who could potentially come back and be susceptible? And so there's 2 ways to deal with these. This is actually a very flexible model, and many of the Diffusion diffusion models are flexible. So you can start incorporating additional components into it. So if people are vaccinated, you could add like some probability of vaccination and some probability of going directly from susceptible to the recovered bin. It doesn't actually, or I guess it's probably better to call it removed, because recovered makes it sound like they had it and then recovered from it. But in fact, they're just removed from the pool of susceptibles and infecteds. As an alternative, there are diseases which you can't, once you're no longer infectious, you're susceptible again, and those are just what are called SIS models. And so people have some probability of moving to infected, and then some probability of moving back to susceptible. Or alternatively, you could have removed, and then after some point, they become susceptible again. So you could add in different pathways into this model. You can also add in so I kept this as simple as I could, but you can also add in demographic changes to the populations of interest. So you could add in, for example, entries and exits into each of these components, and a force of essentially a birth rate and a death rate for each of the categories, and you could continue to get solutions for that. In the network model for epidemics, it's a similar thing. We don't have closed form solutions for it because there's not one single because we don't have a model for, depending on the network, we don't have a model for the network. And so what you would do is you would simulate it, and you would simulate people being removed as you would say, like, this person is no longer susceptible, or these people come and go and add new people in with a rule for adding them into the network. There's actually a good package for that in R, but we'll get there. Does that help? OK. Back to normative diffusion. Okay, so one of the properties of this model, and this is actually a property of all of the network models, is that they ultimately converge to a consensus. So if you run any one of these models long enough, eventually everything is going to kind of stabilize. And usually it stabilizes at some middle value. If you're averaging over everybody, it stabilizes at some middle value. And that middle value could either be a certain fraction of people who have been infected with the disease or a certain fraction of people who have taken up the innovation. Or it could be, like if you're talking about disease diffusion, eventually it'll stabilize at the value of like the maximum number of infected people over time. And so this is actually just a fairly straightforward simulation. We gave everybody a random attitude in X and a random attitude in Y, and then we run this repeated averaging process repeatedly. So after one averaging, you see that they start to cluster in this space. After a second averaging, they start to cluster more. And if you run this model repeatedly, you get the attitudes converge increasingly on a single point, which is kind of this median point. And what this point actually is for the more math inclined among you, the matrix, the row normalized weight matrix, actually forms a Markov chain. So this is the stationary distribution of that Markov chain. So in other words, if you were to run around randomly through this network, so like say you have a network, and you just do this random process where let's play hot potato in this network here. So say you pass the potato here, and here, and here, and back, and so on. If you just move that around randomly over a long period of time, some fraction of the time it'll be at this point, some fraction of the time it'll be at this point, some fraction of the time it'll be at this point and this point. The fractions of the time that it would spend at each of those points is what's called the stationary distribution of that Markov chain. And that's essentially the weights that everybody is going to get that create where this actual consensus ultimately winds up. And so this is actually this notion that things can spread, and these central people are actually the people who get weighted more heavily in this thing. That underlies the whole concept of opinion leaders. And so there's been quite a bit of effort, particularly Tom Valente. This is an article that's worth reading. He talks about the different ways that we can intervene in a network. And one of the key ones that he's pioneered for a long time is the notion of an opinion leader. So these people in red over here are these opinion leaders who you might target and actually say, OK, if we go after these people specifically and tell them smoking is really bad, kids, don't tell your friends that smoking is really bad, potentially they might share with their friends the idea that smoking is really bad. That leaves us, I think that leaves us actually at the point of, OK, actually let me take a quick straw poll, and I won't be offended. How many of you think this is a realistic model? Model. Nobody. OK, or like two people. OK, cool. That's good. I think all models are wrong. Some are useful. So this one has been useful, but there are a number of challenges that exist to it, and that it essentially needs some refinement going forward. So the diffusion literature had been going for a long time, and in the late 90s, early 2000s, there was this whole bloom of simulation studies where people created a lot of simulations. Yeah, John?
Risk of sounding extremely ignorant, but if I was to go back on that, like, why couldn't I have gotten that from like the betweenness centrality of the people in the network to identify the?
I think it's the closeness. I don't remember actually, but yeah, they're quite similar.
Okay.
Well, let's talk offline about that because I don't remember exactly what it is. Yeah. So there's this giant bloom of simulation studies in the late 90s, early 2000s, where all the sociologists realized they could use computers. And they basically simulated, they were like, hey, look, here we can create a network, and we can create some rules for updating, and let's see what the results are. And so let's see what happens when we change the networks, let's see what happens when we change the rules, let's see what happens when we change the seeding process for that, and let's see what happens when we change the size, and so on. And so there was this great boom of studies, and then at some point it kind of stagnated because people kind of got tired of it, and they kind of felt like it was like, okay, we've kind of reached the limit of our of how much additional understanding these models can give us. So we kind of reached the point of saying, like, here here are a set of candidate ways that things can spread between people, and here's how the networks matter. So some things that have come out of that are like the S-shaped curve for the diffusion, the reachability studies that Jim and Martina Morris have done, and things like that, where we've seen, there are some real benefits to running these types of models, but they kind of had stagnated. And so over time, they now are kind of at a point, I think, of resurgence. And as but in order to actually make them move forward, I think one of the things that we're going to have to do is start thinking a little bit more carefully about how this process actually unfolds. So thinking about things like how do friendship influences compound with each other. So I want to take the end of this talk and tell you a little bit about what I see as some current areas of interest in the diffusion literature, and talk about what some directions forward are. And of course, I'm happy to continue to open this up to discussion and see what you guys think of as areas. So one of the first key issues that people started to identify with this is this concept that the diffusion of things, that is, things spreading through a group of people, results in a bunch of people who are connected being very similar to each other on certain attributes. So if you were to just take a snapshot of a school, you would have a cluster of kids who are all friends with each other and they all smoke. And it's not entirely, at first blush, and when we first looked at the data, and when I say we, I mean the field, like 25 years ago, everyone looked at that and they said, oh great, this is social influence. Like, these kids are pressuring each other to smoke. We got to intervene. This is how we can prevent kids from smoking. And then as we collectively thought about this more, we realized that actually a fair bit of that could be selection. So it could be that each of these kids took up smoking at home somewhat independently of each other, either because of a magazine article or because of their parents or just because whatever, and then became friends with each other because they were all hanging out under the bleachers or something, smoking, right? And so the two things could be spurious, basically the fact that the friendships and the smoking behavior are correlated could be spurious, or it could be like a function of the shared selection process. And so the field has spent a long time trying to figure out how to parse out these things. And so David on Friday is going to be talking to us about one of the best methods that we have for parsing this out in observational data, called the Siena model. But there's been a fair amount of pushback about whether or not, to what extent we can actually determine these things from observational data, resulting in a particularly provocative paper by Shalesia and Thomas, which said homophily and contagion are generically confounded in observational social network studies. So in other words, with observational data, if I just take repeated snapshots of kids over time, I am never going to be able to tell whether or not these two kids are friends because or these two smoking kids are friends because they smoked, or they smoke because they're friends. Like, those two things are inherently connected to each other. And in fact, I actually pulled out a quote from this paper because I thought it was pretty entertaining. Because basically they use the example of, if your friend Joey jumped off a bridge, would you jump too? And they go through all the possible mechanisms they could think of in kind of this exercise of reductio absurdum, to talk about what are the different ways that you two both jumping off the bridge could happen. So one is there's some kind of social contagion or influence. Potentially there's maybe a biological contagion, which they might think of as different. So there's some biological disease where you suppresses the fear of falling. Maybe you became friends because you both like jumping off bridges for some reason. Maybe it's a bungee jumping club or something. To the point of where maybe there's a common external cause for jumping off the bridge. For example, maybe you're on the Tacoma Narrows Bridge and it's collapsing, and jumping off it is your best option at the moment. So I think this paper is probably, it's very colorful, and it was very provocative. It's probably a little bit overdone. So we probably should not let the perfect be the enemy of the good, and we should probably say, there is, intuitively we know that we are influenced by the people that we interact with on a day-to-day basis. So just because we can't necessarily just because there are a lot of different possible mechanisms of that, or that could explain the particular correlation that we see in the observed data, doesn't mean that we're necessarily wrong to think that there is a social influence process going on. But it does point the way to better models and better data. So as I said, David will talk about one of the options for better models on Friday. But another possibility is to think of better data. And one of the more exciting things that's going on in the diffusion literature right now is a series of experimental models that's being conducted to basically randomly assign who's connected to who. And so you can randomly, so some people have done this in a this is actually a really clever study, where they look for a natural experiment of ties that are randomly assigned. So these are people who were randomly assigned roommates, and so you're connected to your roommate, but you didn't choose your roommate, right? So that gets rid of the possibility of there being selection into this friendship tie. And so then you can actually look and see whether or not, GPAs change as a result of that. Or if you're feeling particularly ambitious, you can create an entire online community and then randomly assign people to be connected in that online community and say, do things spread between these people who are connected in this online community? So this is, I believe, a health behavior study. And they randomly assigned, basically, like they created this health behavior study. They got people to be recruited into it. And then they randomly, people were randomly assigned into different worlds in the health behavior study. So like they said, OK, if you're online and you get randomly assigned into group 1, then you'll be able to see your nearest friends. Excuse me. If you're randomly assigned into group 2, you'll just be able to see a random set of neighbors. If you're randomly assigned into group 3, you won't be able to see anybody at all. And then you can compare the different groups across time. That is probably the more ambitious route. I remember asking, I asked Matt Salganik about this. I was like, how did you, what possessed you to write your own thing? And he was like, well, it was hard. It was a lot of work, basically. So I think most of the people who do that are now probably in Silicon Valley making a small fortune. But for those of us who are not so inclined, there's a new tool called Volunteer Science that's being run out of Northeastern, which should make it much easier for you to design and run online experiments in a more compartmental way. And they would love to have new people do this. So if you can think of a good experiment for them to run, I'm sure they would be thrilled. A second area that's poorly understood was a question that I got earlier, which is essentially what happens once you've adopted something or once you've contracted some disease. And I think the notion here is that when people actually abandon something is really not, like we have some idea of when people adopt. Like when they're connected to each other, we think maybe they pick it up from their friends, or at least they become aware of it from their friends, and then we don't know. So in part, that's because of a dearth of existing data. Like when people, so for example, if you want to look at when people use Fitbits as a potential proxy for a health behavior, for example, for running, we would know when we have data on when people purchase their Fitbits, but we don't necessarily have data on when they took it off and put it in the drawer. Or like gym memberships, we probably have data on the number of gym memberships purchased, but it's probably harder to get the number of entries into the gym to say like how often did you do it. And actually, a preliminary look at, like, for example, this is just a software in a technology company. If you look at the actual number of cumulative users, you'll wind up seeing the traditional S-shaped curve. But if you look at the number of people who are using it at a given time, you might see it fall off fairly rapidly. And this type of falling off is poorly understood. Another area that I don't think has gotten anywhere near enough study is thinking about experimentation. So what happens when people try out a new thing and then abandon it? So thinking of smoking, we generally treat smoking as a all or nothing event. Like if you have smoked a cigarette once, that's it. But it's actually a pretty wide continuum, right? Like there are kids who try a puff or two, maybe try it for a week, and then throw it away, right? And they never adopt it again. And so we don't really think about what happens. Like maybe social influence is causing the experimentation, but it's not causing the lengthy adoption. Maybe there's a gene-environment interaction. I think we have no idea. And that would be a really exciting area for study. Along the lines of the idea that transmission processes are poorly understood, as we get further and further away from a biological contagion, I think our understanding of the transmission process gets worse and worse. So this past year has seen the US become more and more polarized. And I think everybody has been kind of bending over backwards to try and figure out why that is. Because essentially these models predict consensus, right? And so we don't see consensus an awful lot in the world. Potentially you could say that there's internally consistent consensus, and that is sort of what the models predict. Let me just erase this real quick because I can show you what I'm talking about. So potentially you might have a group of people here and a group of people here, and they converge on a set of attitudes, and each of the separate groups converge on a set of attitudes that have an internal consensus, but a large dissensus between them. But again, this is something that we're not really sure. And we're not really sure how to test the models that we have. And so in a relatively recent paper, the person who developed the idea, the attitude change model that I was talking about, actually just tried to introduce a model with ideological constraints. So if you believe one thing, that implies that something else is true. And then how can we start to explore that kind of space? I think that's a new and exciting way of thinking about this. Another alternative to a similar model is the idea of biased assimilation, which has long been true which we've long known about in psychology, but we haven't done a good job of including into the current models. And so this was a paper in 2013 where they actually try and do that, and they say, like, basically you're going to continue adopting ideas or continuing doubling down on things that you already believe are true. But again, we don't really know what the limits of these are because people do change their beliefs. So it's like it's like a pendulum that goes back and forth and that never quite seems to stay in the center where it needs to be. And so we're trying to figure that out. And a last area, and I'm going to put in an only slightly shameless, actually no, completely shameless plug for my own work, is to think about essentially what do the ties really mean, and how do we think about how things spread along the ties. So when I was talking about the ties that we measure, we talk about kids who are connected by, best friend ties. So like, I'm going to list my top 5 best and closest friends. As Jim mentioned on Monday, there's 2 different ways that we think about networks, really. We think about them as representing a social space, a social position. So like, we could think of like kids in a lunchroom, and there's some table, and they all sit at this table. And on any given day, the people that you name are some random draw of the people at this table. But tomorrow I could go and name a different set of people. And under our model, we would assume that the diffusion process could be totally different. So like one of the things about the network model is that we essentially assume that the ties really matter. Otherwise, we'd be in a random mixing world. And so but more realistically, what we should probably think of, especially a lot of the social network models is some kind of random draw from a social position. So like, I am friends with this cluster of people generally, and who I actually name as a friend on a given day is like a small subset of those people, and that may or may not matter. And so I actually wrote this out as a slightly more detailed way of thinking about this. So you could say that the network ties, first of all, could be measured with error, which is something that we almost entirely don't account for, but is fairly prominent. So there was a discussion in the sociology literature about whether social isolation in America was increasing over the last 20 years. And essentially, this was back and forth in our main journal in the ASR for probably 5 years. And finally, someone came out with an article that kind of settled the debate that said, hey, some of our interviewers learned that the survey takes longer if we solicit more names. So these interviewers who figured that out, just like as soon as the person said, no, I don't have anybody to discuss important matters with, they're like, great, and just like kept going. They didn't prompt, they didn't do anything. So if you control for interviewers, you see that there's no actual decrease in the number of social or in the number of the amount of social isolation over the past 20 years. And this was kind of a big deal. I mean, we spent a lot of time and effort arguing about this, but it turned out to be a data management error. And so while network surveys aren't, I'm not going to go so far as to say like they're totally, they're like riddled with errors, but they can be quite sensitive to the survey mode. Like every data collection instrument can be quite sensitive to how you collect the data. And we need some way of making our inferences robust to small variations in the data management. Another possibility, as I mentioned, is that people could potentially be influenced by people that they're not directly connected to. So Fujimoto and Valente made this argument to say that people are influenced by people who are structurally equivalent. So that is people who are not the cool kids, but like are kind of the hangers-on. Even if they're not directly friends, they're all influencing each other potentially there. So that's some suggestion that there's like a social space effect going on as opposed to necessarily an actual observed effect. And then last but not least, but there is a fairly large amount of churn on a daily basis or in routine basis in network ties. So again, thinking specifically about high school kids, if you interview them twice in 2 weeks with the same survey question, you can get up to, I think, a 50% change in who they're actually friends with. And I remember actually, my friend teaches a high school sociology class, and I went to go give a talk for them. And I said, okay, I know you may not care about this, but I really have to ask you a question. Do your friends really change that often? And they were like, yeah. They were like, do you not remember high school? Like, we have falling out all the time. And I was like, okay. So there is a fair amount of random change that may or may not be real, and on any given day that you may get some people who have fallen out, but then who are close friends again later. So on any given day, you might see this tie, you might see this tie, you might see something else, but you won't necessarily get the same thing every time. So the solution that I want to propose, at least briefly, and I'll talk about how to do this as a practical matter in the lab a little bit too, because what fun is teaching these sessions if you can't push your own work a little bit, is to actually apply some smoothing to the network by modeling diffusion happening over the predicted probabilities of the ties. And I won't get too deeply into actually how specifically we do this. Essentially, we fit a model predicting whether or not there are edges between people. The idea here is that essentially whether or not there's a connection is a 0 or 1, and you can fit a logistic regression to that. There's going to be an entire session on this tomorrow morning. Alex Wasowski is one of the people who developed those models, and he's going to be giving a whole session on this, so we're very lucky to have him be presenting that. But this is essentially, so you fit a latent space model, and then once you get some predicted probabilities of whether or not people are connected under that model, you can actually say, well, maybe things aren't spreading proportionally to whether or not there's a tie. Maybe it's not whether or not I'm tied to this person today or that person tomorrow. Maybe it's just that there's this lunch table, and everybody at the lunch table starts sharing things. So maybe it's just like with some probability, some relatively high probability, I'm connected to all of these people in the lunch table. And maybe that's what things are spreading over. And there's a number of different ways to do that. One way is to do that as an actual predicted probability. One way is to draw a simulated network and see what you get. And we wind up finding that these have a somewhat similar, or have a somewhat different, a somewhat different result in the type of consensus that they converge to. So instead of having people who are isolated in the network just never change their minds or be totally aloof from everything, we find that the model allows them to actually change their minds and be influenced by other people nearby, which I think is an important direction to think about this going forward. So that's a brief crash course in the idea of the diffusion of just about anything in a social network. I am happy to cut it off here and take some questions, and then we'll talk about how to actually run a diffusion simulation model after the jump. Yeah?
Can you go back to a few slides?
Yeah. How far?
I'm not sure I understand this social space.
So the idea is that, so basically you fit a, this is motivated by two things. One is that the ties, there's a fair amount of randomness in the ties that we should be able to account for. And two is that in a lot of cases, what the network that we have is based on the idea of there's a concrete boundary of people who are involved in this network and people who are not. And so what I was hoping to be able to say was essentially, well, maybe this person, maybe there's some probability that these people will be tied to everybody else. Say, imagine you have like the GSS and the important matters name generator. You could say like people in different socioeconomic statuses of different races, different genders, and what have you are likely to interact with each other with certain probabilities. Then you could model a diffusion process looking at the country as a whole as opposed to just within this constrained network. But in addition, within the constrained network, within like the boundary of the network, essentially what you're doing is you're saying instead of having these two ties that are, these two people are strictly connected to each other and these people aren't, you're saying, well, maybe there's some predicted probability of whether or not this is a 0 or 1, and a predicted probability of whether these people are 0 or 1. And maybe that's what should be, what we should be thinking of in terms of how likely things are to spread. Does that make sense?
Would be a predicted probability of a tie given the existence of other ties and, because I don't see.
Let's go back. So in terms of actually generating the predicted probability, Alex is going to be teaching a whole hour-and-a-half long session of that tomorrow. So I'll say that like once you get, like essentially what you're doing is you're putting people in some underlying space and saying conditional on their locations in that space, or more precisely conditional on their relative distances to everybody else in that space. They're all, the probabilities of a tie are independent from each other.
So depending on the personal characteristics, there's this or that probability of a tie.
Yeah, well, you can include personal characteristics, but you're saying basically, like, you're arranging people. So imagine you have some space, and you've got some people here, and a person out here. You would say that this tie is unlikely because these two people are far apart, and this tie is likely because these two people are close together. Again, we'll go through the model. Like, don't worry too much about the models because tomorrow there will be a full hour-and-a-half long session on them. Yeah.
HIV and drug use, and in many cases some participants decided to don't answer the question. So is there a way to deal with that if you don't have the information about this?
I'm sorry, I can't hear you at all.
Okay, I have my research is on HIV and drug use, and sometimes participants prefer to don't answer the question. So it's not a missing data.
Jim's going to hand you a mic. I just can't. The sound doesn't carry well, so I can't hear you very well.
So my research is on HIV and substance and drug use. Everybody knows. And many participants prefer not to answer a question.
Yes.
So you don't have an information.
Right, yeah. So what do we do about missing
data? Is there
data?
a way to deal with this problem in this type of model?
That is a great question. I think the way that we deal with it now is just a standard multiple imputation procedure. So we say that if this person, conditional on all of their other characteristics, how likely was this person to have been HIV positive or HIV negative? That said, that's not necessarily the best way to do it. So if you think of a better way to do it, then we look forward to hearing it. Yeah.
Could you speak to what you think the applicability of, if we find diffusion or just clustering in general, of, say, a negative health behavior for public health interventions, that type of thing?
Yeah. So if you think, some behavior or some negative health behavior is spreading, for example. So like, say you think smoking is spreading. There's a number of different ways you could intervene. One is you could, and actually I'm going to direct you to, let me find that. This article does a pretty good job of summarizing it, but there are a number of different ways you could intervene. One is that you say there's like these people are participating in a negative health behavior. You could try and find the most central person and say, people are most likely, this is the person people are most likely to listen to. That's the opinion leader. Let me talk to them and try and get them to change their behavior, and hopefully they'll spread it to others. You could cluster the graph and say, like, okay, maybe there's this subset of people who we think are at particularly high risk, and we can intervene among that group of people. I'm trying to think of what the others are. What's that? Okay, yeah, trying to encourage. So yeah, so potentially you could try and encourage new ties outside of this. But there's a number of ways that you could think of essentially trying to do this, and I would strongly recommend that you give that article a look. Other questions? Yeah.
You had mentioned some of the options being like randomizing models or trying to create that space. Have you seen them trying to do that more on the analysis side as well, like using econometric?
I'm very glad you asked. We have a person who has done an extensive amount of work, Weihua An, coming in tomorrow to give a lunchtime talk about causal models for networks. And so there has been a fair amount of work looking at those, and I think that should hopefully be enlightening. Anybody else? All right, I think we're about out of time, so thank you very much. Let's take 15 minutes, and then I will tell you how to actually do this as a simulation.